For decades, the space industry operated on a specific economic trade-off. A vehicle like the Saturn V required millions of man-hours and billions of dollars in precision engineering to construct, only to be discarded into the ocean after a single flight. Imagine operating a commercial airline where a 747 is boarded, flown from New York to London, and then immediately scrapped upon landing. The cost of a ticket would be astronomical. To drive the cost of orbital access down, a rocket needs to operate like that airliner. It needs to launch, land, refuel, and fly again within days. Because a reusable ship must carry a massive heat shield, heavy aerodynamic flaps, and tons of reserve fuel, the entire vehicle has to grow. Scaling up the architecture was the only way to carry those reuse penalties while delivering a useful payload, creating the largest flying object in history. Getting that mass off the ground requires the Super Heavy booster. At its base sits a cluster of 33 Raptor engines, engineered to generate over 16 million pounds of thrust. When those engines ignite, they push thousands of tons of steel and volatile propellant straight up, fighting the relentless downward pull of Earth's gravity. The most perilous moment of the ascent comes minutes later. In traditional staging, a rocket briefly shuts off its engines before separating, causing the vehicle to suddenly decelerate as gravity takes hold. To solve this, Starship utilizes hot staging. The upper stage engines ignite while attached to the booster, firing through a vented ring to maintain pressure. This simultaneous ignition prevents the vehicle from losing speed during the transition. Maintaining that velocity translates directly into more mass delivered to orbit. It also means the top of the Super Heavy booster is subjected to a direct blast of supersonic exhaust and the mechanical vibration of 3 engines igniting inches away. Clearing the atmosphere without damaging the hardware is a baseline requirement. The broader architecture of reusability depends on what happens next. Once in the vacuum of space, the objectives shift. NASA's Artemis program relies on a specialized version of Starship to ferry astronauts back to the lunar surface. But lifting that much weight into low Earth orbit consumes nearly all the propellant. The ship arrives in space with almost empty tanks, lacking the energy required to push onward to the moon. The proposed solution is orbital propellant transfer. 2 starships rendezvous and physically dock in orbit, pumping cryogenic liquids in zero gravity. A deep space mission requires 10 or more tanker flights, launching rapidly to fill the central depot before fuel boils away. This logistical chain turns a moon landing into the final output of a high-frequency industrial operation based in low Earth orbit. Eventually, the hardware has to come back down. Re-entering the atmosphere generates friction that heats the surrounding air to thousands of degrees. The windward side of the ship relies on 18,000 silica-based tiles to survive the plasma envelope. Instead of dropping engine first, the vehicle executes a belly flop maneuver. By falling flat, it uses its entire surface area as an air brake, with 4 mechanical flaps actuating to steer its trajectory. This aerodynamic deceleration sheds almost all of the ship's orbital velocity passively, minimizing the reserve fuel that must be hoarded for a landing burn. In its final moments, the ship flips vertical and targets the launch tower. Rather than touching down on integrated landing gear, it hovers just long enough to be caught by a pair of massive mechanical arms. Stripping away the landing gear maximizes the cargo the rocket can carry. Plucking a falling skyscraper out of the air is the ultimate design choice, intended to place the rocket back on the mount for immediate reuse. That is the intended architecture, but the reality of operating these test vehicles is far more difficult. Successfully guiding a battered, heat-scarred ship to a splashdown, or even catching a booster, is vehicle recovery. True rapid reuse is a different standard. Landing a rocket, inspecting the heat shield, refilling the tanks, and launching that exact same hardware a few hours later remains unproven. However, the economics of the program aren't tied exclusively to that ideal. SpaceX does not need to master perfect turnaround to disrupt the space economy. Long before the system reaches full reusability, Starship can simply operate as a highly effective heavy lift transport. This creates a payload-first launch mode. In this scenario, placing cargo into orbit is the primary mission, and recovering the ship safely is a secondary development goal. What makes this economically viable is that SpaceX operates its own satellite internet network. They have an internal demand to lift mass into orbit without needing to convince outside customers to risk their hardware on a developing rocket. This chart illustrates the constraint of the current fleet. While the Falcon 9 has deployed thousands of satellites, the next-generation V3 Starlink units are larger and heavier, requiring the internal volume of Starship's payload bay. For an early commercial flight, the objective is straightforward. After deploying a large batch of these satellites into their proper inclination, the ship executes a controlled disposal over a remote ocean area. The ultimate vision of colonizing Mars requires mastering full reusability, but right now, the program's real threshold is proving that experimental hardware can move into operational infrastructure, one massive payload at a time.